All right, so this is going to be a video on section 9.1, which deals with systems of linear equations. The first thing I want to look at is linear systems of equations. In the three cases, this is what they might look like. So case number one is where my two lines will intersect in a single point. Now down below, here's what this might look like. I'll have maybe one line and then another line that intersects that line, and they intersect in exactly one place. This system has a solution, so it's considered consistent. The equations are not the same thing, so they are independent from each other. Case number two is where my graphs are parallel lines. So parallel lines, remember, are lines that never intersect each other. So we have no solutions here because there are no places where my graphs touch each other. So the system is considered inconsistent because there are no solutions. And the equations are not the same equations, so they're still independent from each other. And then thirdly, we have graphs that are the same line. When I graph this one, it's going to just simply look like one line, but I'm drawing one line over top of the other line. In this case, we do have an infinite number of solutions. There's an infinite number of times that our graphs touch each other. So it is considered consistent because we have solutions, but the equations are the same thing, so they are dependent. One is dependent on the other. And I've just kind of summarized those two statements down below. Equivalent equations, same equations, are dependent, and consistent equations have at least one solution. All right, so then let's look at some examples. Example number one, we're going to use the substitution method. I like to use this method when I have a variable that is either alone or almost alone. So if you'll notice here, my x is almost alone, and it's really easy to get it alone. So I'm going to rearrange the second equation to get that x isolated. And then what I'll do is I'll take that x and I will replace it for the x that's in the other equation. So instead of writing an x in the other equation, I'm going to write what it's equal to. So I'll use substitution here. So in red is where I substituted for the x. Then we'll just do some math. We'll distribute first, and then we'll combine like terms, get the variables on one side, the numbers on the other side, and get y isolated. Now, remember that if my two graphs meet in a single place, this is a coordinate. This is a spot, a point on the graph, an ordered pair on the graph. So I found a y value for example 1, but I still need to find an x value. So I'm going to use this equation because it says x equals. It's not the only option, but it's the one that I'm going to use here. And so I will take my y value and substitute it, do the math to solve, and so therefore my x value is 5, my y value is 2, but remember that this is a coordinate, so I need to write it properly in the courseware. I need to enter it properly as a coordinate. You can check your work by taking both the x and the y, plugging them into both of your equations, and it should cause both of your equations to be true statements. All right, then we have the elimination method. The elimination method is where I actually want to eliminate a variable. Now, before I start on this, imagine that I added like terms. Well, this would give me a 5x. And maybe I wanted to add my y terms, and this would give me a 1y. And then I could add my constants, which would give me a 17. The problem with this is I didn't eliminate one of my variables. So what I'm going to do is I'm going to manipulate both equations so that I can eliminate a variable when I add my two equations together. So the way I'm going to do this is I'm going to first of all choose, in this particular case, I'm going to choose to eliminate my y's first. Mostly because one's already pos and one is neg. And so when I add them together, the signs are correct. I just need the numbers to be correct, the coefficients to be the same. And so what I'm going to do is my top equation, I'm going to multiply by 2. My bottom equation, I'm going to multiply by 3. When I take the top equation and multiply by 2, I'm going to get this 4x plus 6y is equal to -2. Make sure that you distribute the whole way through to all three terms. And then I'm going to multiply by distribution the 3 to the second equation. And you'll notice all of a sudden, now my y's are not only opposite signs, but now the coefficient is exactly the same. And when I add these two together, they're going to eliminate each other. And that's the goal, is to eliminate a variable. All right, so let's go ahead and add our like terms. So we'll add the x's, we'll add the y's, we'll add our constants. And when I do that, I'm going to get 13x equals 52. Well, now it's only one variable, so I can get my x alone. So it's going to be x equals 4. But this is only one piece of my solution. So now I'm going to take my x value of 4 and I'm going to plug it into one of the 4 equations that I have up here. I'm going to choose this one simply because the numbers are smaller, and so it's going to be easier to plug it in. All right, so I go ahead and plug in that x value into the first equation. We'll combine like terms here. So we'll get 3y equals -9, divide on both sides by 3. We'll get y equals -3. And now I'm ready to write my solution as 4, -3. And once again, you can check your work by plugging both of those back into both equations. All right, what happens when we have an inconsistent system? Remember that inconsistent means that there are no solutions. So we kind of have a hint here that these are going to end up being parallel lines. But let's take a look at what that looks like. I chose to use elimination again, mostly because when you look at the variables, none of them are almost alone. And so I chose here to eliminate one of my variables. So I I multiplied the first equation by 2, and then I left the second equation alone. And you'll notice what happens here is that actually all of my variables eliminated each other on the left. So I got 0 on the left is equal to -20 on the right. Now, folks, this is a false statement. 0 is not the same thing as -20. So when I have a false statement where one constant number is equal to a different constant number, this is a false statement. We know that this gives me no solutions, and the reason is because my lines are parallel. Sometimes in your courseware, you might be asked to answer with a null set, or it might just say there are no solutions. In example 4, we are solving a system with infinitely many solutions. So in this particular case, I chose to use substitution method, and I did because of the fact that I have a variable that's almost alone. So I just simply rearranged the second equation to get 3x minus 8 is equal to y. And then I took my y and I plugged it in. I substituted what it was equal to for this y up here. All right, so that's going to give me this. What's in the different color there is what I substituted for y. And now I'm just going to use distribution and combining of like terms. When I combine like terms, I end up getting 0 equals 0. So it's similar to this one up here, except the difference is that now I have a true statement. So since 0 is always equal to 0, or maybe you come up with something like 5 equals 5, or -24 is equal to -24, we would say that this is always true, so we have an infinite number of solutions, and the reason we have an infinite number of solutions is they are the same line. Now the question is how do we write an answer here? Well, what I'm going to do is I'm going to go back up, and I'm going to use this right here. Instead of writing an x value and a y value for my coordinate, what I have circled right now is going to be the y portion of my coordinate. Let me show you what I mean. And so you'll notice that the y portion of my coordinate is 3x minus 8, and then I just left an x here. So both pieces should be written with the same variable, in terms of the same variable. All right, let's go ahead and move to some applications. And before we talk about applications, let's talk about how to solve applied problems. Well, number one, you want to just read your problem carefully. This is probably the most important step that most students just simply don't do. So you want to read your problem through carefully, get the gist of what the problem is about, and then you'll want to reread it. And really what you're looking for is, what is it that you've been given, and what is it that you want to know? What do you know? What do you want to know? Assign variables to represent the unknown values, and write down what the variable represents. In the next question, you're going to see that I did not use X's and Y's. They get confusing. We're going to be talking about Boston and Indianapolis. So I used B for Boston, and I use a capital I for Indianapolis so that I could easily remember which one was which. Step number 3, write a system of equations that relates our unknowns. Step number 4, solve. Step number 5, state your solution. Does it make sense? Is it reasonable? And then number 6, you want to check your answer in the words of the original problem. All right, so let's go ahead. Let's read our question through first. Example number 5. In 2019, the average of the median salaries for the position of environmental compliance specialist in Boston, Massachusetts, and Indianapolis, Indiana was $76,553.50. Now, let me stop right there. Let's make that sentence tons shorter. The average of the salaries is $76,553.50. So the very first thing I'm going to do is I'm going to write exactly that. Remember that average is where you add them together and divide by how many there are. So the average of these two salaries, Boston plus Indianapolis, divided by 2 was the 76,000 number. All right, let's keep reading. The median salary exceeded, the median salary in Boston exceeded the median salary in Indianapolis. Okay, so Boston's salary was higher than the Indianapolis salary. That's basically what it said. By how much? By $11,989,000. Okay, so this is going to make up the second equation. Now, sometimes students get a little confused as to which one to add to. And so what I like to do is I just run a test really quick and I say, hey, if I have the Indianapolis salary and I add $11,000 to it, then I'm going to get the Boston salary. That makes Boston salary higher than the Indianapolis salary. All right, so then we're supposed to determine the median salary for both Boston and Indianapolis. Okay, so in our little form up here, we're basically on step 4 now. Let's solve our system of equations. So the first thing that I'm going to do here is I use substitution. I took my second equation, and in for the B value, I substituted what B was equal to, and that I showed in a different color. So then what I did was I multiplied on both sides by 2 to get rid of my fraction, and I combined like terms from the numerator. And then I'm combining like terms. I got all my constants over on the right side, and then did a little bit of math there and divided by 2. So for I got the number 70,559. So now I'm going to take this equation because it's the easier of the two equations, and I'm going to substitute what my I value is equal to down here. So it says B is equal to I, but I'm going to write 70,559. I'm going to add those two, and I get B is equal to 82,548. All right, so now that was the step 4. We solved it. Now let's state our solution, and we're going to label properly. So my Boston salary I found to be $82,548. My Indianapolis salary I found to be $70,559. And the last thing I'm supposed to do is ask myself, is this reasonable? Well, I look at, and is it reasonable according to what we have in the original question? So my average of the two salaries is 76,000. Well, just guesstimating here, if I average these two, 76,000 sounds about right. And then secondly, Boston's salary was higher than the Indy salary. Well, I definitely have that here. By how much? By 11,000 something, almost 12,000. And that looks about right here. So we're checking our work to make sure it makes sense. We're checking our work to see if it matches up to the original question.